Example 6.7.1. This one says, suppose a 10-year, $1,000 5% Treasury note with semi-annual coupon payments offers a 4% yield when it is issued. What price would an investor pay to buy this note, when it is issued? If the yield holds constant at 4%, what is the price exactly 5 years to maturity? Okay, so we've got the same bond that we're going to calculate the price on at two different points in time, and we're going to see how, if everything holds constant, we're going to see what happens to the bond price over time, and it turns out to be something that is just true of bonds. It's just kind of how they work. So let's start by mapping out our cash flows. On the first one, we have a 10-year Treasury note that's making payments semi-annually. And so we need to map out 6-month periods. So our first tick mark is 6 months from the time it's issued. Second tick mark is 12 months from the time it's issued, and so on, out to 10 years from today, but it's making payments twice per year, so we're going to have 20 total payments, where that is equal to 10 years times 2 payments per year. Right, we know that it'll pay the face value back at maturity, so I'm going to write that down here, and I'm going to leave room above it to go in and fill in the coupon payment that it makes every 6 months, and we'll go ahead and figure that out. So the coupon payment is equal to the coupon rate times the face value. The coupon rate is 5%, expressed as a decimal as 0.05, times the face value of $1,000. And we're going to divide that by the number of payments per year. Since this one's semi-annual, it's 2 payments per year. 0.05 times 1,000 is 50. So this bond pays $50 in interest per year, but it splits it up into 2 equal payments once every 6 months. So it pays $25 every 6 months. All right, so if an investor were to buy this bond today, she would receive $25 6 months from today, another $25 6 months from today, and that would happen every 6 months out until the final payment, where the investor would get the final coupon payment and the face value back at maturity. Okay, the only other piece of information we don't have on there yet is the yield, 4% yield, but that 4%, remember, yield to maturity is expressed as an APR, or annual percentage rate, which does not include the effects of compounding, and our cash flows are happening every 6 months, not every year. So the rate we need to use here is the 6-month effective rate. So what we're going to do is take advantage of the definition of APR, where APR is equal to little r, the periodic effective rate. This is the guy we need, times the number of compounding periods per year. So with this one, we know the APR, it's 4%. We want to know R, and we also know M. There's 2 payments per year. So we just divide both sides by 2, and cancels out. On the right-hand side, we've got 4 divided by 2, which is 2. So our R equals 2%. Our 6-month effective rate is 2%. Okay, so what we want to know there is, what is the price of this bond given these cash flows and that yield to maturity? Okay, so that's the first timeline. All this other stuff is going to be exactly the same on our second timeline. We're just going to bump the clock up 5 years. But it's still going to have the same yield, it's going to have the same coupon payment, and so on. The only thing that's going to change are tick marks. Well, so with this timeline, what we're doing is jumping ahead in the future 5 years, which is 10 6-month periods. And so the beginning time, the 0 on this timeline, is going to be 5 years in the future compared to where we are on this timeline. So we're actually jumping ahead. We didn't even map it out. I just did a little broken squiggly and ellipses to say this pattern continues. So we're actually somewhere in here on this timeline. This bond at this point has 5 years left to maturity. And if it has 5 years left to maturity, that means there are 10 payments remaining. So it's 5 years. There are 2 payments every year. So 5 times 2 is 10 total payments. Our yield is still the same. It's 4%, but we need the 6-month effective yield. So that is 2%. Coupon payments are still the same at $25 every 6 months. And still at the end of the timeline, the investor will get that $25 coupon and get the full face value back. Okay, and we are once again looking for the price. All right, so second step is to figure out what type of cash flows we're looking at. These are both exactly the same because it's the same bond, just the timing is different. So what we have with a bond are the coupon payments, which are an ordinary annuity. They're level cash flows at regular intervals that happen at the end of the period, and they stop. So we can choose the present value of an ordinary annuity formula or the time value money keys in the calculator. And then when we look at the face value, we just have a lump sum. So once again, we can use the present value of a lump sum formula, or we can use the time value money keys on the financial calculator. Okay, so let's map out. We've got an ordinary annuity. The coupon payments. And then we also have a lump sum. That's the face value. We're going to go right to the time value money keys since those are an option. That'll help us work a little faster with fewer chances of error than doing the big long formulas. So let's start with price at issue. So that first timeline that we drew out. All right, the total number of periods in when the bond is issued is 20, because it's a 10-year bond, but it's making payments twice per year, so we have 20 total payments. Our interest rate, since this is 26-month periods, we need the effective 6-month rate plugged in on I over Y, and we figured out that was 2%. Present value is what we're looking for, so put a question mark there. Payment, now we're going to be solving for one of the cash flow keys, and we're putting cash flows on the other 2 cash flow keys. So we need to be very careful with the relative direction of those cash flows and make sure the calculator knows what direction those cash flows are moving. So I'm going to adopt the perspective of the investor, and I'm going to say that payment is a cash inflow, so that's going to be a positive 25, and that means the face value is also going to be a cash inflow. And when we put them in this way, we're going to get back a negative present value, and that's just the calculator telling us that that cash flow is moving in the opposite direction of the other 2 that we plugged in. Okay, let's plug these in. We'll start by clearing out time value money. So everything, all the time value money keys have 0 recorded on them now, and then we'll go left to right to make sure we don't miss anything. N is 20, so we'll type in 20 and press N to store it. I over Y is 2, so we'll type in 2, press I over Y to store it. We'll skip over present value since that's what we're solving for. Payment is 25, so type in 25 and press the payment key. And then future value is 1,000. So we'll type in 1,000, press the future value key to store it. Okay, we have value stored on 4 of the 5 keys, so the calculator can solve the 5th one for us. And we do that by hitting compute PV, so that's what we're looking for in this case. All right, and the price of the bond at issue, given a 4% yield, is $1,081.76, roughly. All right, so if we put that back up on our timeline, that is the price of the bond is the present value of the promised future cash flows discounted at the yield to maturity. Okay, so that's the price at issue. Let's look at the price when we jump 5 years into the future and see what happens to it. So price with 5 years remaining. all of our entries are actually going to be the same except N. N was 20 because we had 10 years to maturity. Now it's going to be 10 because we have 5 years to maturity, but it's making 2 payments per year. So we've got 10 total payments left. The yield is still the same. It's 4%, but we need the 6-month effective rate, so we divide it by 2 and plug in 2 for the interest rate. Present value is what we're looking for. Payment is still 25, and future value is 1,000. So instead of clearing out my time value money keys like I normally would when I go from one problem to the next, I'm going to leave everything in here because the only thing that changes is N. And it stored all those values from the previous problem. So I'm just going to type in 10 and press N to store it. And if I were unsure that those other values are still in there, you can always check them with a recall key. Say recall I over Y and see that it's still 2. Recall payment, see that it's still 25, and so on. Of course, it's going to overwrite what's on the present value key when we solve for it, so it doesn't matter what's there. Okay, so we got all those in. Let's solve for present value again. So we'll hit compute present value. And the price of the bond, despite the cash flows and the yield being exactly the same, has actually fallen. Fell to $1,044.91 roughly. So if we're to put that back up on our timeline, we see that the price of the bond fell. Now, nothing else changed other than the timing. So what is going on here? What happens with bonds over time is that the price will converge to face value. And that's because most of the value of the bond is actually from the face value, because that's the largest cash flow in the bond. And the further off in the future that is, the greater the impact the interest rate has on the present value. Because it's an exponential function. So the bigger N is, the bigger the effect is. As we get closer and closer to receiving that face value, well, the present value of it gets closer and closer to the actual value that you're going to receive. In fact, we can see that drawn out here. We've got 2 bonds mapped out on this chart in the text. We've got one that starts out trading at a premium, like the one we just looked at. And what's mapped out in this graph is what happens to the bond price over time, assuming the yield remains constant. And it moves closer and closer and closer to the face value of $1,000. And the same is true of a bond that starts out trading at a discount. That price is going to increase over time as it moves towards the face value. And holding everything else constant, that's always going to happen with bonds. Now, what will happen over time is interest rates will change, so we'll see the price fluctuations as that happens. But it'll still, even given those fluctuations, it's still going to go closer and closer to face value over time. And that's true for all of the bonds that we're going to look at.